chemistry is kind of like cooking, and a chemical reaction is similar to like a recipe if you're in the kitchen, all right? And if you have cooked anything before, you know that it's really important to have good ingredients, like quality ingredients and stuff. That makes for a better thing. Also, the correct amounts are important. So like down there on the bottom, you can see there's like some chocolate and flour and sugar and eggs and stuff, and they're making a cake, all right? And that's similar to a chemical reaction where A and B come together to make some new compound. Let's call them AB. But if you have too much of one, then sometimes things get crazy, or if you don't have enough of one, it can be bad. Now, unlike in a regular kitchen where if you don't add enough flour, your cake might not be good or something like that, in a chemical reaction, you can have real hazardous conditions if you don't pay attention to these things. So it's kind of important. So you can see in the upper right-hand corner there was definitely a cooking disaster. That can happen in chemistry, but with this chapter, we're going to look at the techniques to avoid those kind of processes and really make sure you take care of business in the lab. So let's talk about a chemical equation, all right? And this is an example of a chemical equations here. This is aluminum reacting with oxygen to make aluminum oxide. Now, because aluminum and oxygen are by themselves and they're neutral, they don't have a positive or negative charge, I would call those elemental forms. So that's elemental aluminum and elemental oxygen reacting to make aluminum oxide, Al2O3. So we need to know the terms reactants and products, and we also need to know how much of each of them to add to make a successful reaction. And you can probably imagine that's what those numbers are for in front of those different things. Those numbers in front of the aluminum, the oxygen, and the aluminum oxide are called stoichiometric coefficients. And you don't have to spell that by any means. It would be one of those. Anyway, spelling was always weird for me. Anyway, stoichiometric coefficients are like a relative amounts. You can think of it as 4 parts aluminum reacting with 3 parts oxygen to make 2 parts aluminum oxide. But instead of parts, you can probably imagine that that's going to have something to do with the moles. Hint, hint, spoiler alert. Anyway, there's another thing too about that reaction. They have a little S and a little G and a little S on the aluminum oxide. And those refer to the states of the compounds. You don't always see them, but they are very helpful. So that tells the chemist that you have a solid form of aluminum reacting with a gaseous form of oxygen. And the thing you're going to make, the aluminum oxide, is also a solid. Now, reactants are everything to the left of the arrow. And reactants are what go into the reaction, the ingredients, all right? And then the product or products are the pieces to the right of the arrow. Those are the pieces you're going to get out. So instead of having a recipe where flour, sugar, water, eggs, whatever makes a cake, where the cake was the product, this is the chemical version of a recipe where we're adding aluminum and oxygen to make aluminum oxide. And we know the states of the matter, we know the relative amounts, and we're going to be exploring more about how these stoichiometric coefficients can really help the chemist out. This is a reaction between phosphorus and chlorine to make phosphorus trichloride. Now, phosphorus is what they call a tetramer. It's P4 in its normal state, and you can see it's a solid. And it's reacting with chlorine gas, you can see right there. And on the product side, what you would make then is phosphorus trichloride. And notice that little L right there, that's the liquid state. That's what that means. So because phosphorus is a tetramer, P4, you're going to see that we'd have to add 6 Cl2s. Now, chlorine is one of the diatomic, have no fear of ice. Clear, brew, it's the clear in that statement, or hunkel briff, that's the chlorine. Anyway, 6 Cl2 making 4 PCl3s. And the numbers and stuff are what we'll kind of deal with in this section. The stoichiometric coefficients, there's a 1 in front of the P4, but chemists don't write the 1. Chemists are lazy, whatever you want to say. If it was 0, you wouldn't put it in the reaction at all. And if there's more than 1, then you definitely put it there. But the 6 and the 4 are stoichiometric coefficients along with the invisible 1. And it also does list the physical states of the reactants and products. So a solid and a gas end up making a liquid. Kind of cool. Don't forget the 7 diatomics. Here's another reaction. This reaction makes iron 3 chloride, FeCl3, from iron and chlorine. Now, again, chlorine, one of the diatomics, have no fear of ice, clear, brew, so it's a diatomic, but iron is not one of those. So notice that iron is listed by itself, Fe, and most elements are by themselves. If they're not the 7 diatomics, they'll be by themselves. Once in a while, I will tell you about something like phosphorus, the P4 we just saw, but that's rare. Okay, most of them, like iron, are by themselves. So in this reaction, the reactants are 2 irons and 3 chlorines. They make 2 iron 3 chlorides, 2 moles of product, as we're going to see. There's a little thing down there. The evidence of a chemical reaction can be observed a lot of times or felt. Heat change is definitely something you can see in that picture up there. That looks like some pretty good energy coming out, so that's going to be one way. If you make a solid, or if you see a gas come out, or even a color change, a lot of times those kind of things mean that there's been some kind of chemical reaction happen, so you can see that something's going on. This reaction is really powerful. This is an example of an aluminum oxide, as we talked about earlier, coming from aluminum and oxygen gas. And notice there on the right, that's a lot of energy. You can really see it. So in the reaction like that, where you have 4Al and 3O2 making 2Al2O3, there's actually a couple different ways to interpret that. One way is on a molecular level, where you can think about atoms and molecules. So if you think about it as 4 aluminum atoms, that's going to react with 3 oxygen or O2 molecules, and those combined will give 2 molecules of aluminum oxide. And that's kind of the way that chemists think about it on an atomic or molecular scale. But what we're going to do most of the time is the second one, and I kind of babbled about it earlier because it's so common in my world, and that those are also mole ratios. So you can also think about it as 4 moles of aluminum reacting with 3 moles of O2 to make 2 moles of Al2O3. And chemists, and you now too, can think about it as either way. On the atomic level, individual atoms and molecules reacting, or you can think about it as the moles way. In the moles way, we have control as a chemist when you're in the laboratory, because you can measure out grams and stuff like that.